Oh, hi there. Thanks for showing up for your learning, everyone. So we had some questions about how do we find the equation of the line that goes through these points, and I want to show you how to cheat so that you know how to do it for all time, and you can do this with more complex stuff. Like if I gave you 3 points, you could find a quadratic, 4 points, and you could find a cubic, a bunch of points, and you could find a trigonometric function to go through it, or an exponential function given a few points. And Desmos can do it all, but you need to know how to get Desmos to do it. So I'll show you how to do these with points. We got the 0.53 and the 0.91. So here's what you do in Desmos. Is you go ahead, you get yourself a fresh Desmos, and you click this plus, and you say, please add me a table. And then you put in your points, 5.3 and 9.1. Okay? And now you can even use this button, zoom to fit my points, and it will show you your points there. If I just get myself a little bit more out of the way, there are our 2 points. So I can kind of prepare a visualization for us. We know that the slope is negative, that b is going to be a little bigger than 3. And then here's what you type if you want to know the linear equation that goes through. We want something of the form y is equal to mx plus b, right? And I could go around and play with sliders and try and get this close, right? And then like play with the sliders, but ain't nobody got time for that to match the points. So this is not actually what you do. Okay, I'll show you what you do. You're going to use that form. I'm just going to give myself a do it anyway. I'm going to use that form y equals mx plus b because I know my data is linear. But instead, I'm going to say y1 tilde mx1 plus b. Okay, y1 means these y values, Desmos. I'm indicating to it that I want those points up in that table there. Okay, see the y1 there? And the x1 is that data set over there. Okay, so y1 is approximately equal to, Desmos, that's what that tilde means, some value m that I want you to find for me, Desmos, plus some value b. And then it tells me negative 1/2 and b is 5.5, which are the same values that I showed you before algebraically, but that's how Desmos would do it for you. And then you could say, well, what if I made this point like 8 and then zoom to fit? Well, now Desmos is showing me the line that goes through those points, right? What if this was 17? And now these are now the values m and b that fit. Mr. Jennings, what's the significance of these R numbers? Okay, the R numbers are telling you how close the mathematical model Desmos came up with fits your data. So this fits exactly if I zoom in here. So see how it bullseyes both points perfectly? So R is 1. In other words, 100% accurate. If I put in a third point, let's say the point, let's say 7, and this will be 8. See how now none of the points are bullseyed by that line? That's now a line of best fit, and it's about 98.6% accurate. You can see that there. It's still really darn good, Desmos is saying, but it's no longer a perfect fit. And our M and our B are really janky looking now. Okay? But that's the equation of the line of the best fit. And so you can use these in science class to get lines of best fit. You can use them to find linear expressions of your data and things like that. Oh, but Mr. Jennings, you got 3 points there. How would we find, say, a curve that would go through those points? Well, do you want an exponential curve that goes through those points or a quadratic curve that goes through those points?
Quadratic.
A quadratic. Okay, so let's find a quadratic that fits that. What's my general form for a quadratic? Oh, right, it's y equals ax squared plus bx plus c. And again, I could play around with sliders until it fits those three things, but no one's got time for that. Let Desmos do it. You would say y1 tilde ax1 squared plus bx1 plus c. And there is the perfect quadratic that goes through those 3 points. Cool. A is 1/2, B is negative 3.5, and C is 8. So I bet if we go over here, we'll find that the y-intercept is up there at 8. Cool, it is. Great. And the vertex is back there at 3.5. Very interesting. All right, cool. So that's the quadratic of best fit. Now, show us the exponential curve of best fit, Mr. Jennings. Sure. Here is our general form for an exponential. Y1 tilde A multiplied by B raised to the power x1 plus C. Okay, there is our general quadratic of best fit. C is the horizontal asymptote. A is that initial value, and here are your coefficients. They look super janky, but hey, we know what they are now. And that also perfectly bullseyes it. Another thing you'll note is that the quadratic had three variables to pick, A, B, and C, and we could bullseye 3 points. An exponential had three variables, A, B, and C. We could also bullseye 3 points. If I had a fourth point to this, it will go to the exponential of best fit or the quadratic of best fit. And I can show you both at the same time there. You'll notice that they are very different curves. The green one is the exponential that fits it perfectly, and the purple one is the purple one is the exponential. The green one is the quadratic. And they're very different, but at those 3 points, they're the same. All right, so that's how you use Desmos to find the equations of your curves of best fit given a data set. So now you can throw data at Desmos and find mathematical relationships. And then once you can do the mathematical relationships, you can apply the tools of this course to those functions. So that's pretty cool. All right, so that is using Desmos to do linear, quadratic, and exponential regressions in a nutshell. Bye for now, everyone.